Okay, please be seated. I'm Boris Altshuler from Columbia University, and I'm supposed to chair this session. And the first speaker will be Helmut Katzgraber from Texas A&M, and it's about quantum versus classical optimization.
Thank you. It's a pleasure to be here. What I'd like to do today is give you a status update on quantum versus classical optimization. And because right now we have the Copa de las Americas and the Euro Cup, I figured I'll keep tabs on how things are going with a little scoreboard throughout my presentation. Now, the results that I will be showing you, and this is a slide that I always like to show, are really at the crossroads from statistical physics, quantum information theory, and high-performance computing. And you will see today that statistical physics is actually quite important when you want to study quantum computing related problems, especially if you want to optimize complex systems. Now, there's a lot of questions we would like to have answers to. For example, can quantum annealers be faster than classical computers? Do applications exist where quantum annealing excels? We've so far studied mostly random spin glass problems, and so far results have been rather inconclusive. And then, of course, what are the limitations of transverse field quantum annealing? Are there things that we know ahead of time will be very hard to overcome if we use this type of optimization technique? And so what we've been doing is we've been developing state-of-the-art classical solvers in an attempt to raise the bar for quantum annealers, but at the same time to also create benchmark problems for quantum annealers. We also refined a little bit the definition of quantum speedup, and I'll get to this later in this talk, just so that we can do a slightly fairer comparison. And one of the things that really we are doing mostly is using statistical physics to analyze benchmark problems. And in particular, we're trying to predict if a problem is well suited for quantum annealing or not. Now, this sounds almost crazy that we're trying to predict something, but I hopefully will be able to show you an example where it actually seems to work. This was done with a lot of people, Sergio, Basil, Sergey, and Helmut at Google, as well as Firas Hamze at D-Wave, Alejandro and Salvatore Mandra at NASA, Stefan Schnabel in Leipzig, and a bunch of guys that work with me. As you see, it's usually hot in Texas, so this is how we dress most of the year. Now, why do we actually need new computing technologies? There was a beautiful editorial in Nature earlier this year entitled Beyond Moore's Law. And I think we all know Moore's Law. I think that's something we can assume. It basically says that the transistor count will double roughly every 2 years. And this trend has been going on for a very, very long time. You can just send a straight line through that, and you see it's still going. This is great news. But there is a piece of information that is often swept under the rug. And that piece of information is that the clock speed has stalled since about a decade and a half or so. So if you look now at the clock speed of the processors, it's basically a constant, meaning that you're reaching fabrication limits. You can't go much faster. So the only way to pack more transistors into a chip is just to add more cores. The other thing that a lot of people don't think about is that if we ever want to build an exaflop machine, we will need gigawatt power. And so it's a little bit like, electricity for a town or running a computer, which is going to be a very difficult issue to tackle. And so this has led to many investments, Google, IBM, Microsoft, and many others. And of course, the big question is quantum the technology of the future? Now, we do have now commercially available quantum devices. There's all kinds of things. However, the current state of the art when it comes to computing are special purpose computers. And I think we all know exactly which machine I'm talking about. It is the big black box from D-Wave Systems, Inc. As you know, it's a special purpose quantum annealer, so there's only one thing it can do. It can optimize problems mappable on its topology. And there have been sold a few of them. And I think that this is still a groundbreaking result. Building such a device with so many qubits is not easy. I've heard that it will come out with a 2,000 qubit chip in the near future. And so this is, in my opinion, a huge technological feat. Now, what can it do? Well, it can minimize problems in cubo format. In other words, if you write it as a quadratic form, something like an Ising model, Once you can encode it onto the fixed topology of the chip, known as chimera, and within the machine constraints, for example, precision. And if you want to see some of the ideas that we have been developing about how to improve chimera itself, I encourage you to look at the poster by Mark Novotny later today. Now, one thing that I want to talk about very briefly is how the machine optimizes. And this is important because what I will do is I will do an analysis of the performance of the machine. And for this, I should remind you how it works. And actually, the way it optimizes is sequentially. Now, you might wonder, why is there a big X on here? And the reason is that the way the D-wave optimizes was developed about 7,000 years ago in the Neolithic era. And the Germans, of course, discovered that if you anneal a piece of metal, it's more malleable, you can make a better axe, and you can more efficiently bash each other's heads in. Now, we don't want to do this here, but basically we want to just use the same approach numerically, and this is known as simulated annealing. You have a Hamiltonian or a cost function, you stochastically sample it. Once the system is thermalized, you cool it, and you do this according to some annealing schedule, for example here, a linear schedule, and then you hope to find the optimum. In fact, if you anneal infinitely slow, there is a theorem that proves that you should find the optimum. However, that is, of course, not very efficient. Now, when you have a problem with a rough energy landscape, say like a spin glass or a complex optimization problem, then simulated annealing has the potential of getting stuck in any of those metastable states. And to overcome this, what people have done in previous studies is very simple. You just do multiple restarts. In other words, you rain down on the landscape until you hit the jackpot. This allows you to do statistics and then basically figure out if you found the optimum or not, at least with a given probability. Now, the D-wave device does basically the same using quantum annealing. This is what we all hear, except that instead of quenching thermal fluctuations, what you actually do is you just quench quantum fluctuations. It's basically the same thing. Now, the nice thing is that you're not limited to a local search, and potentially, if barriers are thin enough, your system might be able to tunnel through the barrier and find the optimum. And the way it's done in D-wave 2x is transverse field quantum annealing, where you just apply a transverse field, it doesn't commute, and there was a beautiful animation earlier by Vasil that showed this. And then basically you reduce this quantum fluctuations d according to some given annealing protocol. Now, there have been many, many attempts to see if this machine can do something that classical computers cannot do. And I think that the most recent results that are most promising, and they were presented in detail earlier by Vasil, are the recent results by the Google/NASA team, where they showed that there can be a very large speedup for very carefully tailored problems. I'll show you again the results, and I'll just focus on the 50 percentile for simplicity. And of course, the result is simple to summarize. If you compare, first of all, just absolute numbers, this here is around 10 to the 13, this is about 10 to the 5. So you have roughly a 10 to the 8 speedup for the largest system size of 945 or so qubits. However, this offset is not the most important thing. The most important thing is actually the slope of this curve, because asymptotically, this is what is going to determine who wins the race. And you see very nicely that the simulated thermal annealing has a much steeper slope than either quantum Monte Carlo or the D-wave device. So this is, in my opinion, really the first strong signature that quantum approaches scale better than classical approaches. And what this means is 1-0 for quantum. Now, let me say a little bit more about Google's weak, strong cluster instances. As I said, Vasil mentioned this already before. I just want to look at it from the spin glass point of view. And that is, you have what they call weak, strong clusters. Basically, they're all ferromagnetically coupled. You have one field that is stronger than the other. And this cluster here is just basically kind of like the Siamese twin to this one. And this one over here then connects to the rest of the system in the network. Now, the important thing is to zoom out as far as you can and just look at this rectangle as one object. And if you look at it, what you get is basically a spin glass with positive and negative interactions on some kind of network topology. Okay? The only job that these weak, strong clusters have is to basically fool a thermal annealer into a metastable state. Quantum annealer, however, might be able to overcome this problem. Now, there are some potential issues. If you compare now quantum annealing to simulated annealing, well, simulated annealing is known to be an extremely poor optimization method. There's far more state-of-the-art algorithms out there. And don't ask me for a reference. This is just for me doing this for the last 10, 15 years. Some Monte Carlo methods are extremely inefficient the second you turn on strong uniform fields. And the reason is that flipping individual spins becomes a very hard task. So we figured, let's do a fair comparison and use what is known as population annealing Monte Carlo instead of simulated annealing. Some computer scientists here might know it as particle swarm method. And the idea here is that we want to use something that is sequential. In other words, you have a control parameter, either quantum fluctuations or temperature, that you tune from a large to a small value. And at the same time, we know that population annealing is pretty much unaffected by external fields, which is phenomenal if you want to simulate spin glasses. So how does this population annealing work in a nutshell? Well, let me remind you, simulated annealing, you easily get stuck. You run it in repetition mode. And what you then get basically is the optimum. In population annealing, you do the same, except that you run all these runs in parallel at the same time. And at each temperature step, you call the population according to the Boltzmann distribution. What this means is, if some of these instances are stuck in a metastable state, they get killed and replaced by fitter instances that actually are getting to the true optimum. And so what this means is that basically your effort gets reshuffled, and then you get to the optimum much better. So again, the way it works is you just perform capital R simulated annealing runs in parallel. Okay, typically R is, say, 10 to the 5, 10 to the 6. It's a very large number. And then at each temperature step, you do a resampling of these guys. You kill off some, and you repopulate with others. So think of it as a little bit as a mixture of a genetic algorithm with simulated annealing. And then you do a handful of Monte Carlo sweeps just to make sure that Boltzmann is happy. Now, if you simulate spin glasses at a finite temperature, you will find that population annealing is as efficient as the state-of-the-art parallel tempering Monte Carlo. It's an extremely good method. The other nice thing is that the numerical effort is the exact same as simulated annealing. The resampling step is really very small overhead. So it's fair to compare population annealing to simulated annealing. And you can just switch off on this side the resampling step, and then you just have simulated annealing run in parallel. And it outperforms simulated annealing in repetition mode. Now, I can demonstrate this to you. What you see here is data for a three-dimensional spin glass with 512 sites and 1,000 sites, so roughly the size of the D wave and the D wave 2x, okay? And on the horizontal axis, you have the population size, or the number of times you ran simulated annealing in log 10 base, and this is the percentage of solved problems. And you see that if we run a population of 10 to the 5, or we do the simulated annealing 10 to the 5 times on these problems, then population annealing finds all solutions, simulated annealing only finds about a third. If we increase the system size by a factor of 2, you see that simulated annealing wasn't able to solve anything at this size problem, whereas population annealing clearly does solve still all problems. So it is a much more powerful method, and it is sequential. So let's toss this into the whole picture. And I just highlighted the line for population annealing. These are, again, the results by Google. And you see very nicely that the slope, of course, is less steep than simulated annealing, but still far from the scaling we got with quantum Monte Carlo or the D wave 2x. So one could see this as additional evidence of some quantum advantage. In other words, 2-0. Now, population annealing is just one method. What if we now open the drawer and pull out all possible methods that we can think of, basically a long laundry list of algorithms, and see how do they compare against all of those? And so before I show you the list of algorithms, I'd like to just very briefly refine the notion of quantum speedup such that the comparison later is a little bit more apparent. Until now, in the paper by Ronoff et al. In 2014, it was introduced that we have provable quantum speedup. In other words, you can prove that there is no classic algorithm that will do better, say Grover search. Then was strong quantum speedup, where you compare to the best known classical algorithm, say Shor's algorithm. You have potential quantum speedup, where you compare to a set of algorithms, and these, of course, can be short-lived until somebody finds a better method. And then there was what is called limited quantum speedup, where you just look at speedup over a classical counterpart. And so we decided to take limited quantum speedup and just refine it ever so slightly. We first introduced limited tailored quantum speedup. What does it mean? It means that you know the structure of the problem. So you're not receiving a problem which has no structure. You can look at it and say, ha, if I use this trick, I can abuse the structure and find the optimum faster. Prime example, the Hamza de Freitas-Selby algorithm, which basically exploits the tree structure of Chimera. Then we have limited non-tailored quantum speedup, and I would call this the gold standard. These are generic algorithms. They assume nothing about the system, but they are the fastest that you can find. And then there is limited sequential quantum speedup, which basically is a sequential method like population annealing, simulated annealing, quantum annealing. And the motivation for us to do this was to basically perform a better description of the benchmarks. So we went through this long list of algorithms. We looked at tailored ones, for example, the Hamza de Freitas-Selby algorithm, a superspin approximation that Zheng Zhu, who will talk after me, introduced, which is basically something rather brutal. You take each of the weak-strong clusters and you call it one spin. In other words, you just take this and replace it by that. And instead of solving a problem with 900 and something variables, you end up solving a problem with maybe 12 variables. Obviously, you'll find the solution instantly, okay? And then there's a hybrid cluster method by Salvatore Mandra, Venturelli, etc. Then you have the non-tailored algorithms, for example, population annealing, which basically is sequential but is not tailored, parallel tempering with isoenergetic cluster moves. This is the solver that we use. And then we use some other things like replica Monte Carlo. And then, of course, we compare this to simulate annealing and quantum Monte Carlo. Let me show you the results, and I ask you to not try to discern what is what in this spaghetti plot, okay? These are the simulations with all these algorithms. And I just highlighted two lines. One is, again, the D-wave result, or on the machine, and this is quantum Monte Carlo. And you see that these here are simulated annealing, population annealing, but all the other ones are pretty much comparable to the performance of the D-wave device. Now, we decided to do an asymptotic scaling, in other words, exclude the small system sizes. The reason for this being that it seems that there is a double scaling in the D-wave due to noise, and Salvatore Mandra will give a talk this afternoon at 3:30, actually addressing this point in detail with this beautiful, simple model that he developed to address this. Now, because we're doing an asymptotic scaling, again, all that matters are the slopes. We're going to try to fit an exponential with some coefficient b, and we also tried to do this with a polynomial prefactor to normalize it. And all that matters is this exponent b, because that will tell you what the slope is of these individual lines. And what you see here are these exponents b. Now let me walk you through it. There is red blobs and blue blobs. Forget about the blue blobs. This is where we assume there's a polynomial in front. The red blobs are this coefficient b here for the different algorithms: simulated annealing, population annealing, D-wave 2, quantum Monte Carlo, hybrid cluster, replica Monte Carlo, parallel tempering, HFS, superspin. I'm done. And the important thing now is I should color those in. And of course, a smaller value of b means a better scaling, in other words, a faster method. And you can see very nicely, I drew a line here through the D-wave results, that within the category of sequential algorithms, clearly quantum Monte Carlo and D-wave, sorry, I drew a line to quantum Monte Carlo and D-wave outperform population annealing and simulated annealing. However, when you even use non-tailored algorithms, in other words, generic methods that we developed, you see very nicely that they perform better. So in other words, I would say that what we have here is sequential quantum speedup. And so what this means is 1 to 2. Now the next important question is, does the scaling persist for large system sizes? And this is going to be a little bit technical. Okay, this is where the statistical physicist in me comes into the picture. And it starts with something that Helmut mentioned this morning, this P of Q thing. And so what we do is we need to find an order parameter for a spin glass. And the natural order parameter for a spin glass is the overlap between two copies of the system. Why is that? If you look at a ferromagnet and you lower the temperature close to 0, then what you will see is that either all spins are up or all spins are down. So you just look at the picture and you know right away the system is ordered. In a spin glass, the spins will freeze randomly in space. And so if you just look at a snapshot, you will not be able to tell if it's in the ordered or disordered phase. So what you do is you simulate 2 copies of the system with the same disorder, and then you compare spin by spin, and we call this quantity the spin overlap Q. And you see that if these 2 copies agree, then for low temperatures, Q should go to 1, modulo this normalization, and for high temperatures, it goes to 0. So it's a natural order parameter for the problem. Now you can now measure the distribution of this quantity. And again, I'd like to remind you of the ferromagnet. If you look at a ferromagnet at very low temperatures and you look at the distribution of the magnetization, either the spins will be all up or all down. In other words, you will get 2 delta peaks at roughly plus minus 1. Okay? But if you now increase the temperature, magnetization will average out to 0, and due to the central limit theorem, you will just get a Gaussian centered around 0. In a spin glass, you have the same behavior at high temperatures. However, at very low temperatures, you can have dominant states that form and form different basins in the energy landscape. In other words, instead of just having 1 peak at plus minus 1, you can actually have a multitude of peaks. And the position of these peaks, here you have 3 examples, red, black, and blue, strongly depends on the disorder that you chose for that particular problem. And so we've been staring at these functions for a long time, and if you have no linear terms in the field, it's spin reversal symmetric, so it's enough to just look at half of the distribution. And you can show that if there are many features, then likely you will have something that corresponds to a wide barrier, and I don't have time to go into all the details of this. And when you see thin, sharp features, then likely you will have thin barriers that show the potential for tunneling. And I'd like to also mention that if you typically have a single wide feature, then it could be a problem without any features. What do I mean by this? Basically something like a ferromagnet, something parabolic and simple, modulo some little bumps. Now I swept a lot of details under the rug, but we did very careful studies here in this first paper with Burcu a few years back, and you can very nicely show that this complexity of this function also correlates very well with the autocorrelation times of state-of-the-art algorithms like parallel tempering. So we went back now and measured these quantity for the Google instances, and what we found is typically 2 types of problems. One that looks like this, a single sharp needle peak that is away from 1, and the other one basically looks like a tooth with maybe 2 or 3 peaks that are really close together. And so what this means is, and this is based on more than just looking at pictures, that whenever you have a very thin peak, you have either a thin or no dominant barrier. And typically, the Hamming distance for that is about less than 16, and we know that D-wave will have some tunneling advantage if the barrier is thin enough. However, when you have double or triple features like this that overlap, the barriers are too thick to see any tunneling. And so what we can now do is we can plot the fraction of problems that have a thin versus a thick barrier. And what you see very nicely is that with increasing system size, the fraction of problems with wide barriers becomes dominating. In other words, the bigger you make the system, the more the spin glass backbone will dominate, as Vasil said in the morning, and you will eventually lose your scaling, and the quantum advantage will vanish for large n. So sadly, we're tied. Good. Now, I showed you these results, and now the question, of course, is can we use this for something else? And what I'll show you now are very new results that we have just produced, and I'll just show you one case study because Zheng will show you a whole palette of problems that we've analyzed. And this is weighted partial max-sat. It's just a typical constraint satisfaction problem. Max-sat is the problem where you want to determine the maximum number of clauses which satisfies a given Boolean formula, and weighted partial means that you satisfy all clauses and maximize the sum of the weights of the soft clauses. And you can encode this into a cubo-like Hamiltonian and then basically solve this with whatever solver you want to solve. Now, what does the P of Q look like for this very particular problem? Well, you get something that has many spikes. And when you have many, many thin spikes, it's suggestive that if there is some kind of tunneling, you should be able to tunnel through these spikes. And so what we did is we sent these problems to Sergei Isakov. He ran them using simulated annealing and quantum Monte Carlo. And what you will see in the next slide is basically the speedup of quantum annealing over simulated annealing measured in Monte Carlo sweeps. And what you see very nicely is that, first of all, this is a logarithmic scale. And for about 90% of the problems, you needed about a factor of 1,000 less Monte Carlo sweeps in quantum Monte Carlo than in classical Monte Carlo. In other words, we were able to predict that this type of problem would be perfectly suited to run on a quantum type architecture. In the meantime, we've tested, of course, everything we can get our hands on. Random spin glasses, well, they're random, but if you mine the data according to the features, again, you can show speed up. Same thing for vertex covers, 3-SAT, 4-SAT, graph partitioning, circuit fault diagnosis, et cetera, et cetera. So in other words, we have now an opportunity to basically go in and decide ahead of time if a problem might benefit of quantum speed up. And this is really great, because it comes back to what Helmut said. You can do a run a test of the problem, and of course, there's still a lot to be learned here, and then decide if you farm it to a silicon-type machine or to a quantum device. And again, if you want to learn more about all these things here, just stick around for the talk right after mine. So I would say, given this information, it's a 2-3. Now, the last thing I want to address is something very new that we did, and this is what we call fair sampling. And so fair sampling, everybody gets a beer, basically is very simply defined as the ability of an algorithm to find all solutions to some degenerate problem with roughly the same probability. So if you run your algorithm, and you know the problem has 17 different solutions, and you run this 10,000 times, and you make a histogram, you want to make sure that these 17 bins are roughly filled the same modulo Poissonian fluctuations. That means your algorithm can find all solutions to a problem, and not just the minimum. And this is very important, because sometimes solutions are more important than the minimum. Think, for example, at SAT filters, where you need many uncorrelated solutions, hash SAT, or if you want to do contingency testing, or, for example, if your problem has some other constraints that are not part of the optimization procedure, think solving a traveling salesman problem, but then it happens that your trucks are parked in a place where you're not right now, so you would like to have a better solution that matches this additional constraint. So the gold standard for any optimizer is find the ground state fast and reliable. A much stronger test is find all minimizing configurations equiprobably. And back in 2008, 2009, I did a very nice study with Yoshiki Matsuda and Hidetoshi Nishimori, where we looked at first at a toy model of 5 spins. Here, dashed line means antiferromagnetic, solid lines ferromagnetic. And basically, what we found is that this has 3 degenerate solutions, modulo spin reversal symmetry. And when you now look at the probability of finding these 3 solutions as a function of annealing time, if you have a transverse field quantum annealer, what you find is that solutions 2 and 3, you get 50% of the time, but solution number 1 is exponentially suppressed. Similarly, if you now say, well, let's use a more complex driving Hamiltonian like the one shown over here, suddenly this weird behavior goes away, and you find all 3 solutions with 1/3 probability, which suggested the transverse field quantum annealing might be biased. So we thought, let's do a more thorough test and use a model that has a really nasty collection of solutions, and that's the so-called fully frustrated Ising model. It's just an Ising model, but every second row here is antiferromagnetic. And you see now that every plaquette, this model has no disorder, but every plaquette is frustrated. So a system with 36 spins already has about 45,000 different degenerate ground states. And when we ran this, again, using quantum annealing, you see very nicely that some states are exponentially suppressed. Okay. However, if you were to do this with classical methods, this is not the case. So what about quantum annealers? Well, we ran experiments on the D wave, and we chose our disorder to be in 5, 6, 7. Plus minus, and we modded those interactions in a way that there's no floppy spins, and we can very carefully control the degeneracy to be 3 times 2 to the k, so 6, 12, 24, 48, etc. Okay, and then for fixed C and K, we studied the distribution of ranked ground states. Now, I don't want to bother you with the details of showing every single plot. I can just show you one characteristic plot here. These are experiments run on the D wave for different number of ground states. And you see very nicely that, again, the data are biased. In other words, there is an exponential suppression of certain states. And this, of course, is very bad news because this means that transverse field quantum annealing is an exponentially biased sampler, and this also suggests that we need to think beyond transverse field. So this leads basically to a tie, but a tie in quantum mechanics is nothing else than a coherent superposition. So we're basically stuck with this. And with this, I'd like to thank you for your attention.
Thank you very much. Questions, comments?
So we have microphones now, so if somebody doesn't want to come all the way up, Austin and I will hand you a microphone.
Thank you. I can see that this method would work for multi-spin interactions, for multi-spin terms in the Hamiltonian. And I wonder if you have a feel for how much harder the calculations get as you add more and more multi-qubit terms.
So I don't have a feel as to how much harder they get, but they do get harder.
Okay, you don't know how much?
No.
But
I can't quantify it at the moment, no.
More questions? Again.
Let me come around.
Okay, thank you. So you finding that the distribution of solutions is not uniform when you use the transverse field Ising model, the transverse adiabatic algorithm. But I think what would happen if you varied the paths? I mean, I would bet that if you had randomly sampled your paths, you would flatten out that distribution.
What I can tell you is that, so we have no, I mean, obviously on the D-wave you cannot really do that. And in some ways, my point was basically we need to think about more clever things, better driving Hamiltonians, the influence of thermal noise, say with this quantum parallel tempering, better paths, etc. But these results, as you mentioned, were done with many gauges. So despite applying gauges to the system, the bias was still there. So my guess is that unless you happen to find the optimal path, which is a measure 0, it's not going to do much for you. Yeah, sure. But I don't think that it would help too much.
I have to disagree with you. Gauge transformation is a classical operation, whereas changing path is a quantum operation. It takes you to different corners of the potential. And also the second comment is I would encourage people to listen to D-wave talks because we can do multiple paths. And we have seen the effect of that in optimization. I encourage people to listen to those.
Oh, cool. That is news to me. So I'll look forward to that.
So I know with the D-wave machine that there's some fuzziness in each individual coupling from systematic random variations, et cetera. Do you know how much that affects the fair sampling?
Well, if anything, I would expect it to help. You see, because if some fluctuation or error is applied, basically, you are kind of breaking that bias introduced by this strong transverse field at the beginning of the anneal. So, I mean, obviously, in the end, the question is, are you still solving the right problem because of the fluctuations? But I think that for something like fair sampling, and we haven't tested in detail, we can, of course, simulate this, any type of fluctuation will likely be of a slight help, in my opinion.
More questions? Yeah.
Can I, sorry, I'm on. Great talk, Helmut, thanks very much. So we've also been looking at the backbone of samples coming from the system. You mentioned during your talk, you could imagine using this as an analysis technique to determine which instances to send to the quantum annealer. But one of the things we've observed is that, getting a good estimate of what that sort of spectrum of the background looks like can actually be very complex. And in fact, we've been finding that using the quantum annealer to try to heuristically estimate what that is actually one of the fastest methods for that. Do you agree?
No. Sorry, I just had to say that.
Yeah.
So I mean, this is one metric. We also have other metrics that we have developed and that we're currently testing, especially based with population annealing. What I like about this is just, a feature of the problem and not the algorithm. But we can also use algorithms to basically get a hand on how complicated a problem could potentially be, at least in a for a sequential method. And that is at least a fair comparison now to a quantum annealer. And there, the experiments we have done with that metric that is extremely quick to measure, we have promising results suggesting that there's a strong correlation, in fact, even stronger correlation than with this P of Q. But having said that, and this is something that I always keep saying, there is really very little to no understanding about the spin glass physics, especially when it comes to the order parameter distribution. And everything that we've learned so far has just been literally, often by trial and error over the last 2 years. You know, by tailoring a problem to do a particular physics outcome and then seeing what it looks like, and then using that to go on problems where we don't know the outcome and try to do predictions. So there is a lot to be learned from all kinds of points of view.
Thanks, Helmut, for the very interesting talk. Back to the benchmarking of the weighted partial max sat problems and the speed up that was predicted. Given the fact that QUBOs are equivalent to weighted max 2 sats, I was curious to know what model of weighted max sat problems did you try?
Yeah, it's a complicated thing. You see, I wanted to sweep the details under the rug. Zheng is going to show you more about this in the next talk, but there are some XORs in there, and yeah. It's not just a standard max 2 sat, but at least it's a whole class of problem, you see. Before, we were saying, here are spin glasses. Look, these 5 are fast, these 100 are slow. Here we have something where it doesn't matter what we generate, it's almost always fast.
Maybe last one and short question, please.
Hi. You said that a fair comparison is only if you, it feels fair if you compare the quantum annealer to a non-tailored approach. Now, I definitely understand that feeling, but usually you know the architecture of the quantum annealer, so it feels like in the real world we'll always be able to come up with a tailored approach.
I agree and I disagree with that. So we can produce problems on the Chimera architecture that we can predict will be extremely hard for quantum annealing, and also for tailored algorithms like the HFS method. So you see, there's ways, and if you look at the problem, yes, you know the structure, but you just see random bonds. You cannot really discern what we did to it, yet it will be really, really hard.
Thank you very much again.